everyone, welcome. I appreciate everyone making the time. I know how busy everyone is, and especially those that have come some long distances. I think you're really going to enjoy the program today. We've got a couple people that will be talking to you, including Tim Show and Simone. Before we do that, real quick, I know some of you know Avid pretty well and have been working with Avid for years, and some of you don't know Avid as well, so I thought I'd just do a quick introduction. Again, my name's PC Romano. I'm the president of Avid Solutions, and we're an industrial automation company. And basically, we bring the best-in-class technology plus industry domain expertise and try to marry those two things to identify your top opportunities and challenges, and then implement the best solutions possible. And so, as we've grown the team and built the team, we do bring in people with both technology experience as well as domain expertise. And so earlier this year, we brought Tim Shope on board, and Tim will talk a little bit about his background and kind of our view on all the things that are going on. But every so often, I think there's a significant shift that happens, and today I think there's a few of those. So Tim will talk a little bit more about those shifts, but more importantly, how those can deliver real value. You know, it's one thing to apply technology. It's another to have a good return and good value derived from it. So thanks again for joining. Look forward to catching up with all you guys later. And now I'll just turn it over to Tim.
Good morning. As PC said, my name is Tim Shope. I've been in the industry for, I can't believe it's over 35 years, or 25 years now. Started with a company called MeasureX, which was acquired by Honeywell. Worked with them for about 16 or 17 years, primarily in the pulp and paper industry. A lot of the things that I did there was around quality control, quality measurement. It was early adoption of a lot of analytic stuff, SPC applications. It was pretty advanced technology for what we did back then. As part of that, I learned how to do return on investment calculations, how to go prove out quality improvements and what that could mean from off-spec reduction, energy consumption reduction, raw material, yield improvement, etc. From there, in around 2006, late 2006, I got the opportunity to go be an end user and spend quality 6 years in a paper mill. And they call it a mill for a reason. It grinds up stuff, and including people, right? It's 24 hours a day. You are, Todd knows what I'm talking about. He was one too, right? So you get the 2 o'clock in the morning call, you get the 10 o'clock Saturday morning call, you got to go spend your weekends troubleshooting, fixing stuff, repairing stuff, etc. And that experience kind of changed my life as far as what I thought automation and control is about. And I'll get to that a little bit more in just a second. From there, I went to Rockwell Automation. I was there for a little over 7 years. Did a number of roles inside Rockwell. One was the North American pulp and paper industry leader. The other was a engineering manager for a couple of years, managing the delivery arm for the heavy industries in Rockwell. So we did Plant PX delivery into pulp and paper, metals and mining, and chemical industries. And then most recently, I was the North American pre-sales director for Schneider Electric. So I had the domain experts from the Foxborough DCS, Triconics SIS, the cybersecurity guys, some of the hybrid PLC guys, as well as the modernization and migration consultants. I was also their North American EcoStruxure domain lead, so everything that's coming out of digital plan around Modicon and 580, their whole digital transformation structure, I was the process domain lead for that for a little over a year. So, why am I at Avid and what am I doing here? Digital transformation is kind of a, I don't know if you want to call it a buzzword today. I think everybody has some digital strategy of what they want to be and what they want to do. And to me, it really comes down to how technology is evolving at a rapid velocity today. I mean, you can think that you're on the bleeding edge today, and 6 months later, you're almost having a refresh. I mean, if you look at how IT has progressed in the past 20 years, you're going to see the same thing happening in automation today. You talk to, or you follow people like Sandy Vassar on LinkedIn, and he will tell you that digital transformation is not around the technology, or not about the technology. It's using the technology to enable you to fix real world business challenges, right? So if you look at that technology, how many people got an iPhone in their pocket today? Anybody doesn't have an iPhone in their pocket? You, Samsung, still got a smartphone, right? Nobody's carrying a Razor anymore or a flip phone, are you? Anybody got a Nokia?
I want to go back.
You want to go back?
Don't get emails on that.
You want to disconnect. So you do not want to be one of these connected devices, right? We look at the number of devices that are connected today. Even in my own personal life, and Miranda and I have been married since 2003, which at that time we really put in our first wireless router inside our house. Up until then, we were all plugging in and everything. When's the last time you plugged your laptop in? I can't remember the last time. I mean, I used to carry a Cat 5 cable around. Now they don't make Cat 5 anymore, so it'd be a Cat 6. But I used to carry those around. I haven't had one in my bag in probably close to 10 years now, right? So when people start talking about connectivity and connected devices, it's not only being able to extract data or aggregate data and consume data, it's the ease, the ability to do that, right? Whether it's over Bluetooth or it's over Wi-Fi or it's over LTE or cellular. This connected devices is creating a wave of technology enablement in industry and automation that we have not experienced before. Right? We have been traditionally a hardwired, very, very conservative automation business. And so the next thing that's going to empower with all those connected devices is now we have so much more line of sight to what's going on inside of a process, right? As you start getting to lick and stick sensors and low code integration of those, now you can aggregate data from multiple sources. You can start leveraging multiple different algorithms in a compute horsepower that's completely in the cloud. You don't have to stand up a server, right? It's literally plug it in, and within 30, 40 minutes, you are collecting data and assimilating that data. It's amazing what's happening. And it's just going to get faster and bigger every day. So as I mentioned around changing business challenges, the digital opportunities, which are the technologies, and right, what do you want to do? How do you solve business challenges with these technologies, and what does it empower you to be? My former mill manager, one of his biggest things he always talked about was getting the right data to the right people at the right time, which was a novel concept in 2006, right? That meant, right, alarm management, alarm rationalization, a few other things that we had not done for years, and we did all that. And then we started doing some basic analytics. He allowed me to acquire some technology from MajorCon, which was process doctor, process monitor. I could build multivariate analysis. I could build a model of a paper machine in a good running state, and when it deviated from that, I could set an alert and I could know that something had changed, and it would drill down to what had changed. But that was me sitting in a back room building a bunch of models. Today, with machine learning, if you have a conception of what you want to look at, you can deploy AI and machine learning. It'll do most of that for you in an automated sense. So while I was in the paper mill, I kind of transformed a little bit myself. When I left Honeywell, I was the advanced control nerd of the year, or maybe decade, right? This opportunity gap that everybody talks about, right? Reduce the variability, expose the opportunity gap, take the target shift, reduce raw materials, energy consumption, build a multivariable control that looks at your process holistically, that can drive you into a constraint corner that optimally or optimizes your profit. And this is all real, this works, this is amazing. The incremental profit that you can capture out of a good running, well-tuned, economically driven process. I will never tell you that this doesn't work. You can find millions of dollars of return to do this day in, day out. But the problem with it comes is in the middle of the night, when this unmanaged electromechanical asset fails, all those savings, all those opportunities are gone, right? Unscheduled downtime erodes your OE, erodes your profitability quicker than anything else in a facility. Is the demon that we got to move out of manufacturing in America. And so As I mentioned, I had major con process doctor, right? We were monitoring most of our PID loops. I knew when a valve was sticking. I knew when a loop was undertuned or overtuned. I knew when it was costing me money. Even when it was oscillating the valve, all the way down to the amount of air consumption that valve was using because it was oscillating as opposed to smoothly operating. So I could do all that cost decomposition up here. We had intelligent instruments in the field, but we did not have intelligent I/O in any of our DCSs, right? So it was all up to an operator with a handheld to go out there and extract that data and then go take it back to our AMS system. So that was happening about once every 2 months, maybe. We'd get a new update of any kind of calibration. So we had major issues in that span and scale in the DCS didn't always match span and scale in the instrument, right? We may have an instrument span 0 to 100, and we may have the square root in the instrument, and at times we put a double square root in the DCS because we didn't know somebody had squared it out here and squared it out here, right? So when you try to do mass balance equations and energy consumption equations, if your instrumentation is not right, or somebody just went and recaled it last week, none of your mass balances add up. When you look at an advanced control strategy, if somebody goes and changes the slope on an instrument, they just change the gain in your control algorithm. Happens all the time, right? So heart and integration of those intelligent devices are solving that problem for us in a process environment. But I didn't see, and I worked for Honeywell and Schneider today, up to date, and they're building some more intelligent in the intelligent motor control centers, right? You can now connect to that drive. You can see motor power consumption, full motor load amps. It has some scalable analytics in it, right? It knows that the fans have run at 60% for the past 2 years, and you're probably going to have the fans fail, etc. But I didn't see anybody on the market space that was able to take high-speed data of what's going on with this electromechanical device and do what ExpertTune and Control Station and MajorCon have done for PID loop monitoring and health anywhere in the market space until I got exposed to SAM4. And this stuff is amazing. It is a great component to plug in when you can monitor your PID loop health. Now you can monitor the electromechanical health in near real time, right? And you get predictive analytics of unscheduled downtime coming 3 to 4 months in advance, right? So when I found out about this stuff, I made, was it one call I made over there? And we chatted for...
Best call of my life, too.
Very flattering. Anyway, my vision is to combine the electromechanical data that's available today in conjunction with what's in the intelligent motor control centers with the process data so that we get a holistic vision and view of this asset's health, performance, and its viability to survive so that we don't have unscheduled downtime. This is some amazing technology that can drive unscheduled downtime out of manufacturing. So that is, it's been my pipe dream for about 9 years, and pretty excited to see it happen. So, as I mentioned, I'm with Avid now from a system integration standpoint. The coolest thing about that is not being tied to a platform or to a vendor's technology. It allows me the ability to go look for answers like SAM4 and how we can integrate it with some other partner platforms, Ignition, Seek, Camo, OSI. You know, combining these technologies in a low-code integration standpoint allows us to develop very, very profitable, very easy to deploy solutions for you guys. So that's kind of my pitch of why I'm here. Simone is going to come up and tell us about SAM4 and why he's here.
Thank you, Tim, and thanks all for being here. PC, thanks for hosting me today. My name is Simon Jagers. I'm one of the founders of SemioticLabs. We're a Dutch company founded in 2015, and we focus on predicting if, when, and why critical AC motors and rotating equipment fails. And today I'd like to share with you, first of all, starting off with sharing with you the story of one of our clients, because as Tim says, it's not about digitization per se, it's about delivering value based on these new technologies. Later on I'll take you to some of the slides that go into a little bit more detail as to why we do what we do and how we believe that provides value. and I'm most comfortable with the technology in and of itself. As a data scientist, you really want to talk technology as much as possible, so I'll spend some time doing that as well. During the presentation, if there's any questions from your end, please do not hesitate to ask. I'd like this to be as interactive as you'd like it to be. So, starting off, the CEO of one of our large clients in the steel industry announced in 2017 that they were going to increase their investment into digital technologies. And the reason for that to do that was they wanted to build better quality products. They wanted to increase safety for their staff, and they wanted to improve reliability of their plants. And that, obviously, with all the developments in sensors and IoT and machine learning, there's a lot of possibilities to actually go ahead and do that kind of stuff. And one of the projects they focused on right from the start was monitoring a conveyor system in a hot strip mill. And the hot strip mill produces flat sheet metal, such as used in cars and so on. And that conveyor in that system had about 260 AC motors that move sizzling hot plates of steel across the production process from A to B. And just around 15 to 20 of those motors failed each year, to the tune of about €1,000 per minute. So that's fairly expensive if that happens. And in those type of situations, what they've tried before is they've tried traditional technologies such as vibration technology, which is, I suppose, in condition monitoring pretty much the standard nowadays, right? So, and the principle behind it is if that machine starts to fail, what it'll do is it'll start to vibrate in a markedly different manner. So if you measure those vibrations and you look at what's happening, then you can detect failures as early as possible. But you can install a vibration sensor on a hot strip mill conveyor, but it will not last very long if those sheets of metal are, I looked it up, around 2800 Fahrenheit. And about 1000 Celsius and up. So the sensor simply will burn. So they were a bit hesitant to work with us, but anyways, they installed our technology. And what's different from what we do relative to others is we both try to detect failures as early as possible using sensors and machine learning. However, we do not use vibration sensors, but we measure electrical waveforms from inside the motor control cabinet. So you can effectively detect failures on both your motor, your frequency drive, and your application, albeit a conveyor or a pump or whatever, using those electrical waveform analysis. And as said, I'll dive into the technology a little bit later as to how that works. From our perspective, and also from our clients, it was a great success. So throughout the first year of implementation, we detected 12 out of 13 failures. So that's a good start. It's not perfect. Our goal is to completely eliminate downtime. We didn't succeed in that, but looking at 12 out of 13 is a very good score relative to the more traditional technologies that detect 70, maybe 75%. We were well over 90%. So we were happy with that. And as a result of the test, we're now monitoring pumps across Europe and so on. So, the client was happy as well. But when you look at the value I think that we provide in those situations is that we have a technology that is easy to implement. It installs inside the motor control cabinet and not on the asset in the field. It has a very high accuracy rate, well over 90% across the board. I believe we're now at about 93% of failures that we detect in the field in production environments for clients such as Schiphol, Volbeck, Newell, formerly known as AkzoNobel, and a decent set of clients across many industries. And that is, all of them are primarily concerned, first and foremost, can you help us eliminate the cost associated with unplanned downtime? Depending on industries and depending on many factors, but typically you're looking at 35k to 45k per hour, and these costs can be massive. It's not just the additional maintenance costs, but it can be loss of revenue. And I'm sure many of you, or probably all of you, have at least a figure in your head: what is an hour of downtime costing me in terms of cost, loss of revenue, and so And I think one issue that is sometimes overlooked, I thought Tim had it on his slide, but is the fact that these costs are likely going to rise moving forward. And I think there's two reasons for that. First of all is due to automation, Lean Six Sigma process optimization, what happens is we'll make more money per hour because we're more effective at doing that. But it also means that if we have downtime, we're losing more money relative to a healthy functioning state. But what's also sometimes overlooked is that at least in the Netherlands and across, I suppose, Western Europe, 35–45% somewhere there of technical staff will retire in the next 5 years. That's a huge issue because, I mean, I'm not intimately familiar with the situation in the United States, but if you look at Europe, young people nowadays, they want to learn how to code an iPhone app and not learn a proper trade. And the problem with that is that iPhone apps do not replace broken bearings or fix a broken pump. You have to have people doing that. So from that perspective, I think, and we subscribe to the notion that technology is here to help people work more effectively, work more safely. And it's necessary to. Looking at these numbers, they're high and they're likely going to rise. Now, as mentioned, our system is measures electrical waveforms. In fact, it's a plug-and-play system for predictive maintenance that has some prescriptive elements in it. So we measure electrical waveforms from inside the motor control cabinet. We do some local pre-processing and send them to the cloud for 24/7 analysis of those electrical waveforms. And we then turn that data into actionable information about the condition, about the performance and energy consumption of those connected assets. And I think, interestingly enough, the energy part is gaining traction because we're working on essentially providing as much value from that data as possible. So it's not just around condition monitoring, which is where we're focused on now, but moving forward, we'll see more and more of these connected digital applications focusing also on energy reduction processes. And that's something we're working on with domain experts as well. But you can think of our solution as a plug-and-play solution that detects upcoming failures at an early stage, installed inside the motor control cabinet. Value proposition for RMN is typically what you would expect from these type of from these type of traditional applications. 70–75% of reduction in frequency of downtime, unplanned downtime, reduction in maintenance costs. I think we're outperforming that, and that is all due to the fact that an electrical waveform simply has so much more to offer than just vibration. There's upside of vibration as well, don't get me wrong. I mean, if you want to detect a bearing failure 9 months in advance, we're not going to do that for you. We're likely more 2, 3, 4 months in advance. But by and large, when you look at the information that's in the electrical waveform, that's astonishing. And one key thing to remember here as well is that around 30% of motors, or 1 in 3 failures, has an electric element in it when it comes to AC motors. And that's obviously where we excel. We measure electrical waveforms, we pick them up early, and you simply will not catch most of them using vibration, because you can only pick it up at the moment that the electrical issue is reflected in a physical manifestation, and that will be very late in the process. So there's a structural benefit as well. Now the value proposition is being accepted by, for instance, ArcelorMittal, where we monitor conveyors and pumps and so on. We work with Vopak, monitoring pumps inside ATEX zones. We work with Heineken, where we are monitoring AC motors that sit well inside of filling stations, so it's very hard to reach that motor using traditional technology. And we work with Schiphol, the Amsterdam airport, the Dutch airport, the pride of Holland, I may add, where we monitor conveyor systems inside the basement. And what they have in common, all of these clients, is that they benefit from the fact that we do not install anything on your asset in the field. I think I said it before, right? But it makes sense to repeat it, because when you look at a conveyor in a hot strip mill, it's very hot, your sensor will burn. When you look at sensors inside ATEX zones, explosion-free zones, I think the American term is ATEX or IEX. Looking at you, Mike. Are you familiar?
I couldn't tell you.
Sorry, don't want to punch you out. Anyways, there's rules and regulations around installing additional equipment inside these explosion areas, right? And you can buy them. It's a little bit the same as buying stuff for your bakery or Vogue. Just the fact it'll be much more expensive than anything else. But wiring in those situations can easily cost you up to $1,000 per 3 feet or per meter or something like that. So if the motor control cabinet almost by definition sits outside the ATEX zone, so you can imagine that's a huge benefit of doing it this way. Hard to reach places such as we do at Heineken, very easy to install. If you can't install a sensor, if you can't get the raw material for this kind of analysis, which is data, you really don't have a lot of use for your system anyway. And if you want to do it at scale, it makes sense that if you can install in 30 minutes relative to 3 hours, and a very robust sensor network as well. So I have a vested interest in confessing that this is, in my view, very useful. I hope it certainly is for you as well. But please remember, there's many situations where it makes sense to install inside that MCC. And well, I think I've covered this for all. One thing to remember here is, as briefly mentioned before, we're all about extracting more value from the system, from that data source, and we're happy to work with Tim and Mike on actually achieving it, really integrating our background, which is around data analysis, with domain knowledge. And I think moving forward, that's where we see the real benefits of these technologies. As Tim said, it's not about technology, it's around providing value, and the shortest route to providing value is integrating the best of both worlds. Technology is very good at processing very large amounts of data, but how to do it and what to do is something that must come from you guys. So if you have data science in your firms, I encourage you to interact with them and tell them, what's your problem, how do we think we can go about it. That's very valuable for us as well. Right. Ultimately, I think, as Tim said, it's about providing value. So how do you present the data? It's not, and I think that needs to be highly actionable. This is what we show online, and I'll, at the end of the presentation, I'll briefly go into the dashboard for a moment. But what it's really about is we got some motor nameplate information, we call it the motor dashboard or passport, and we have an indicator of the health. Green means good, red means there's an immediate issue that requires our immediate attention. For us, yellow means we're monitoring it for you. There's no need to act now, but if you can choose, if you have, time to inspect 10 motors, why not do the yellow ones and not the green ones, so to speak? And orange means please do check at your convenience. Not today, not tomorrow, but if next week or so would be a good time to inspect. We have an indicator of what goes wrong. So in this case, we have an indicator that there's an issue with the rotational frequency, and there's 2 or 3 causes associated with such increases. It can also be highly specific. For instance, we detected a bearing failure, and it's we advise you to inspect your bearing, and so on and so forth. Some additional information around performance trends and all these things, and these dashboards are available on any device that's connected to the internet. Now, do you have any questions so far? Please go ahead.
Actually, I have a few of them. So, you mentioned over and over that it does not require any retrofit of existing equipment. In other words, you don't need to do anything. You just can go ahead and install.
That's right.
And what about a large percentage of your equipment is near obsolescence? Can it still work, or do you have like a preferred, this is too old, like from 30, 40 years ago, and we cannot really work with it? Is there any kind of requirement like that?
Well, I understand your question to be, what if Do we have preference as to how old the equipment is? Does it work on older equipment too?
Correct, because some of the older equipment may not be necessarily amenable to all these monitoring and sensors and whatnot, so is that possible?
In fact, it's what we love, because if it's old, it means it's typically more likely to have a higher failure rate, which means we can easily improve the value of the solution.
So in terms of deployment and age of the equipment, it's not an issue.
No, by and large, it's not. You're right.
The other thing is that you have a better than 90% success rate in determining potential failures, right?
That's a fair statement, yes.
And you said that the time is more in the order of 3 to 4 months. Is that pretty much across the board?
No, that's not across the board. And thank you for asking me. You asked me, you have over 90% success rate and the time to live or between your alarm and your projected failure, right? So by over 93%, I mean, if from every 10 failures of your assets in the field, you can expect us to detect 9.3, or from every 100, 93. Now, the time to failure, the time between the alarm and the projected failure event, varies based on the failure mechanism at play. For instance, if you have an unbalance, it can run for quite a while with that unbalance before failure. Same for some of those bearing failures, a couple of weeks, couple of months, easily or longer, where there is a failure, but not a catastrophic failure in the sense that the machine stops working. Electrical failures can move from, igniting or starting to a catastrophic downtime in very short time frames. So 3 to 4 months is for some of the, for instance, for imbalance or soft food or those kind of things. Electrical failures really depends on it, but maximum 3-4 months. Typically, let's go with 2, 3, 4 weeks or so. So it will provide you with enough time to take mitigating actions, but it's not months. There's certainly, you need to spring into action. Yeah.
And then the other thing is that sometimes, given the fact that what you were talking about, your SAM for being mainly applicable to rotating equipment.
Mm-hmm.
So sometimes the rotating equipment is mainly a motive force, let's say for a belt or something.
Yep.
And if there is an issue with the belt, so it starts slipping after a certain number of hours of service,
Yep.
would the system be able, the sample would be able to detect things like that? So it's not necessarily the driver, but the driven piece perhaps detect certain things in terms of variation in RPM because there is slippage, or maybe more. Does it have that capability?
Yes, so the question is, and I'm repeating it for the viewers at home, for sure we detect failures in both a belt, slipping belt, we would detect that, or in the driven equipment as well. I was planning on doing this a little bit later, but this is a very good moment to briefly introduce how we do what we do, why it works. So at the start I said vibration works based on the principle that if something is failing, it starts to vibrate, and if you measure that vibration, you can analyze it and look at patterns in that data that indicate, for instance, bearing failure, because it will vibrate, have additional energy at a different frequency than when it's soft food, something like that. Now, when, for instance, the pump starts to cavitate, are you guys familiar with the cavitation of a pump? All right, for Mike then, Mike Keel. When a pump starts to cavitate, there's implosions in the fluid. And if it continues to cavitate, at some point those implosions will eat away at your pump housing, and your pump will fail. Those implosions, they introduce a vibration that you can measure on the outside of the pump. What also happens with those vibrations is that they will travel from the axle of the pump through the coupling to the axle of the motor. At the motor, they will disturb the air gap that sits between the static part and the rotating part of the motor. There's a little air gap between it. When you disturb that air gap, you introduce wrinkles on your sine wave. And those wrinkles, that's what we measure. and using Fourier transforms, we turn them into frequency domains. And from that moment on, the analysis is not 100% similar, but it's very similar to traditional analysis. Only, I mean, we automate that kind of stuff using AI and self-learning and so on. But so that's the principle that we use. Vibrations turn into ripples on your sine wave, which can be turned into frequency domains and which can be used for analysis. This is a very long intro to your question, which means that if a belt is slipping, we calculate RPMs based on the waves and so on, so we can use that. If a slipping belt or if a belt becomes loose, it starts to vibrate in a different manner, we pick that up as well. Usually the question is also, to what extent can you detect failures in your driven application? And that depends. If there's a lot of intricate designs between your motor and your application, it will get very hard, typically. Because what needs to happen for us to detect it and also to classify it is it needs to travel from your application through anything that sits between to the motor. So luckily for us from a business case perspective, if you have a very big gearbox sitting between your motor and your driven application, you can build a business case on the gearbox from a financial point of view. So it makes sense to monitor, because if the gearbox starts to fail, there will be a huge cost and you can monitor it. What's maybe unlikely is that the vibrations as a result of failing of the application, reach the motor. But so typically we have a process in place where before we start implementing, we want to make sure we under-promise and we over-deliver. So typically we'll review the list of assets that's up for monitoring, so we can give you a very good idea of where we are on that front. That's a presentation in and of itself. But thanks for the question.
So can I take that, what you just said, in terms of the waves, extrapolate from it, that the waves then become unique to certain things that could be going on. Therefore, you can presumably say, okay, if it has this behavior, is because it melts. If it has this kind of behavior, because presumably if it is right at the motor or the pump itself, it has a certain sinusoidal. But as you go further down, you can say, okay, because of the degree of acceleration or change in the not only amplitude, but the period and so forth, maybe it's this and this. In other words, you can use it to some extent to zero in on the part that's about to.
That's exactly right. So your question is, can you use the waves to identify or classify the failure mechanism at play? And that's exactly right. We call them fingerprints of failure. So a bearing failure will look very similar to other bearing failures, but not to soft foot, by and large. I mean, there's huge different types of bearings and so on. So but you can use the form of the waves to identify what's going on in your machine in most cases. Not always, but in most cases. And to that I would say, one of the benefits of modern cloud-based technology is that provided you have your security in order, but once you have that, you can leverage learning at gigantic scales. Just spoke to Mike yesterday around how that translates into additional value, the fact that you learn a lot. And I compared it to traditional situations where you would have a level 2 or 3 trained vibration specialist. And if he is on the road 200 days a year, and if he does 10 units per day, and he visits them once every month, he has like 1,000 or 1,500 or so individual assets that he inspects 4 times a year. And over the course of his career, we came up with a number of 30,000 or something like that. It was late in the evening. Anyways, we concluded that number of lessons that he derives from his work, that we do the same kind of measurements every single day. Now, I think humans are much better at creative stuff, and so it's not a one-for-one comparison, right? But the fact of the matter is that we analyze so many samples on a day-to-day basis that we can really look at the intricacies involved with those failure mechanisms and use them to improve that classification for everybody involved. So it's you can look at it as a learning factory upscale. So it's an interesting development.
So you pretty much described that you're doing ESA for the most part,
ESA?
electrical signature analysis.
Yeah.
So how are you powering your transmitters? Are they wired or wireless?
Yeah. Here we are. This is what we installed, just to make it very visual. So, and schematically, it's like this. We install current and voltage sensors between your frequency drive and your ASIC, or direct online as possible too. That's an analog signal. They feed into these orange boxes. And the orange box, what it does, it turns the analog signal into a digital one. And then maximum of 10 of those are connected via an Ethernet switch to a gateway that does a local processing and connects to the platform. And the connection is made via 4G, cable, or wired internet.
Okay.
That's it, basically.
All right. How often are you pulling a spectrum?
It depends. Typically once an hour.
Okay. And you don't run out of storage space in about 3 days by doing that?
Well, no. The storage is almost free online. So we use AWS Cloud. It's all, so there's a huge data set being built up there, but it's almost free.
Okay.
So
there are two issues with the nuclear industry and
Yep.
that right there. The first one is it's 8 to 10 times more expensive to run wires than wireless sensors. So that's one issue that we're dealing with. The other one is it's a cloud-based system, and in the
Yep.
nuclear industry, just put a big X through the word cloud and don't even mention it in public, otherwise you'll be strung up.
Okay.
So my two questions. One, how could we adapt this to use a wireless transmitter? I think that would be pretty easy. The hard part is how can we install a system like this? Because it looks great. I'm a big proponent of ESA. Can we install a system like this on an on-prem server farm, whatever you want to use, whatever you want to call it? Will it work that way?
that's a very interesting discussion to have, and I'd like to take that offline. The answer is yes, but not now. The reason for that is we're working with some of the Dutch, governmental branches that are in the business of safeguarding the country. They do not like the word cloud as well. I suggested to call it a platform, but that, they said, well, it's not about the word per se. So, well, there you have it.
Right, cloud's a fancy term for someone else's computer.
Exactly. So, the agreement that we have is that we will build the system to work on premise at some point in the not too distant future. The thing is, it's fairly expensive to do. So the conversation, if the technology would be interesting to you and you can provide us with the scale that it makes sense for both yourself and us and our other to do that, I would welcome that. There's no technical risks, there's technical challenges, let's go with that. And to tackle those challenges, you need sort of let's call it enough units to justify the cost of doing that. But it's certainly possible, it's certainly on the roadmap, and it's a good conversation to have between us.
Okay, thank you.
So to talk about the wireless question, can you talk about where these devices are typically mounted, MCC, control panel, that kind of thing, and what kind of wiring you might avoid with wireless?
Yeah, the only requirements we have there is that we install between your frequency drive and the asset. And typically that's in the MCC or any location where it's not exposed to extreme heat, moist, stuff like that. So if it's a safe location to install them, that's fine. This creates, these orange boxes, the data acquisition devices, are connected to the gateway using Ethernet, Cat6. We still have them in our bags, Tim, but just for this purpose. So it creates a local network that's sort of a local private network for our system, and then it goes to the cloud. Yeah, and these cables can be I think 75 meters, that's 200 foot or 250 feet between the switch, and then between the switch and the gateway another 75. If it's longer, you run the risk of data quality issues. So you create this network, and you know, every shop floor has a different setup, so you have to, it's very flexible as to how you install it, as long as it's a, you know, a safe location. Does that answer your question?
Yeah, you know, he mentioned the nuclear industry, how expensive it is to run wire.
Yeah.
Conduit. So you could potentially locate all these devices near each other.
That's a fair statement, and the gateway is a cost of about $1,000. So if it makes sense, if you need more gateways, then you can you know, look at what's the wiring cost versus is it worth to spend some additional funds on more gateways, so I have to wire less. So I have to wire less. Not more wire.
You can put all these CTs and PTs right at the MCC or the bus, run them to a single gateway out with one transmitter, and off it goes.
Exactly. Yeah. So that's the first thing. Yeah. Right. So this is the hardware setup. Let me just briefly review what I skipped. See if it makes any sense to repeat. Oh yeah, delivery. So by and large, on site, we install, as you saw in the slide here before, inside the motor control cabinet or anywhere that's safe and sound and so on. We turn the electrical waveforms into digital ones, or the analog waveforms into digital ones, and then we have two families of algorithms that we use to process that data. So we use anomaly detection to detect patterns that are abnormal, that are anomalous relative to the healthy state. So when we detect an anomaly, what it means is that we see patterns in that data that we cannot explain by the load, the speed, or any other factor that we measure for that motor. And it means that something is going wrong that we did not expect. So you could call it an early warning. Something's wrong, we don't know what yet. What we also do is simultaneously we run classification algorithms, and they are continually looking for known fingerprints of failure. So, as mentioned before, the pattern that is associated with bearing failures is different from, you know, a soft starter that's broken or cavitation and so on. So we continually look for patterns that closely resemble known fingerprints of failure. In the event that we detect an anomaly but cannot classify it automatically, that's, for instance, when our data science team starts to investigate. Because computers are very good at classification, but they're not very creative. But the data scientist may say, well, you know, based on my experience analyzing these type of patterns, I know this is, you know, bearing failure, but there's something slightly wrong. Let's review, let's talk to our client, and let's make sure he gets the message and see if it's correct. By actively labeling those data, by actively looking at those anomalous patterns that we could not classify automatically and doing it manually, we build out this sort of this library of fingerprints of failure, and you know, you get increasingly more robust at detecting specific failures across a diversity and multiplicity of situations and so on. Now, whether we detected it or classified it automatically or manually, we will make sure to send you an alarm. So one of the early lessons of what we're doing is that most of you guys who have an operational responsibility to run a shop floor or to run a machine did not sign on to watch our dashboard day in, day out. You have a job to do, right? So we kind of expected if we make a pretty dashboard, our clients will sit back in awe and look at everything that we present to them. That did not happen. So whenever there's a failure, if it's not an urgent failure, we will send an email. If you don't get a response in 24 hours, we will send another email. And at some point, we'll just start calling. If it's urgent, we'll call you right away. because we really think that it is our job to make sure your machines keep running. That's what you're paying for, right? So we actively alert our clients, but we also present that information in the dashboard that's either online or on your phone and so on. Yeah, a couple of, how it looks in the field. We've gone over this. I've touched on those. Oh, right. So here are some examples of these fingerprints of failure. So again, these are the waveforms, and using Fourier transforms, we can then turn them into something that's very similar to the frequency domain as you would expect from traditional vibration monitoring. And again, the process is vibrations disturb the air gap, create wrinkles on your sine wave, and using Fourier transforms, they show up with extra energy. Oops, there you go. So if you look at those two, healthy versus cavitation, not much to look at with the human eye, but if you start overlaying them, you see some additional energy here and there that is very indicative of cavitation. And we have more of those. For instance, a broken rotor bar doesn't happen a lot, but it does. And when it happens, you would see some additional energies here. And it's not just that we look at the individual patterns, but also how they, how they develop over time, and we take into account rotational frequency. So, for instance, if you have a bearing or a coupling issue, you're likely going to see some additional energy around 50 and 150% of the rotational frequency. Those kind of things or those kind of models are in play too.
Quick question: does it matter if you have a, say, real old style MCC versus smart MCC? Does it make a difference?
So your question is, and again for the viewers at home, how old the MCC is?
Yeah, if the smart brick MCC versus no, does it make any difference for your system, or does it matter?
No, I don't think so. I mean, there's going to be exemptions to that question, but by and large, I wouldn't expect it to make any difference. No. Another example here, soft foot. You see markedly differences in these patterns from the healthy to the failed situation. Please.
So, I mean, these aren't radically, I understand the differences, but radically different from one another. I've got a building, 1 million square feet, it's got 2,500 pieces of equipment in it.
Yeah.
How many times am I going to have a manual setup versus an automated setup? Percentage?
As to how we detect it?
No, your setup. Some of them are automated, some of them you have to do the manual fingerprint. Out of 2,500 pieces of equipment, I have to do it 10% of the time, 50% of the time?
You don't have to do anything. First of all, it's our job to do it for you. The way the process works is if we, let's throw out a couple of numbers. First of all, our job is to detect failures. And we want to do that with as many true positives, so accuracy matters, which means you want to detect as much failures and not miss any of them. And you're also looking at false positives. How often out of your 2,500 assets do you have to go to that asset because we say so and there's nothing wrong? And you want that to be as low as possible. And that's very low. I think we had 6 or 7 times in 2019 that we asked somebody to go to the asset where it wasn't necessary. Now, the reason for mentioning that now is my point is that if we say there's an issue with your piece of equipment, it always makes sense, or by and large makes sense to go look at it. So that in and of itself is the value we provide. We then will ask you, what your technical team, what did we find? Were we right about it? And we can use that information to improve the algorithms. But you don't have to do that. If you're up for it, we'd appreciate feedback. So when you go to the asset, you can count on it that there's a failure. So in that sense, it always makes sense to inspect. And the feedback is a request, but not a requirement. Thank you. Does that answer your question?
Well, that answers a part of it. I mean, I was really looking at the set point. So I've got, of those 2,500 pieces of equipment, there are some that are alike, many that are not, right? A lot of them being one-off.
Yeah.
Do you have to, the automated setup
Yeah.
versus the manual, having the setup, what's the percentage? Is it 90% of the time that the automated setup will work out, and 10% of the time that you have to do a kind of a manual defining of that unit?
From your perspective, it will be 100% automated. The system is built with scalability in mind. So that's why we spent 3-4 years perfecting that part, because we can't. Our mission is to work with, to eliminate unplanned downtime for those very large sets of assets that were sort of forgotten, right? The very big ones you'll have Lilink here, you have GE, very good stuff, very expensive. We're here for the small man or the small motor, so to speak, and we provide. But the only way we can do that cost effectively is if we have zero to very little customization for those assets. So we'll install and we start to monitor. For your 2,500 assets, I would say that out of every 10 failures that we present to you, 4 will be very precise. Regardless of, I'll take my chance on your 25 without knowing them, but I'll say by and large 4 of them will be very precise, where we will tell you it's a bearing or it's a coupling. Another 4 we will present you with 2 or 3 options. So we see unbalanced, we think it's your coupling, but it also could be soft foot and so on. And I think 2 of them will be, we know it's mechanical or we know it's electrical, but we're very sorry at this moment, the only advice we can give to you is inspect. So from your perspective, out of every 10 failures, 4 will be precise, 4 will be somewhat precise, and 2 will be. And for those 2 is where feedback is most valuable, but from a deployment, installation, or implementation point of view, that's very scalable. We start and we start learning. That doesn't mean that from your 25%, I'm sure there's a couple of, from our perspective, freakish assets where we will need to take some time. I mean, 2,500 is a lot, but by and large, it's designed to scale, including implementation. Is that a... Right, thank you.
Simon, you mentioned small motors versus big motors.
Yeah.
And you may address this later, but do you want to talk about voltages or horsepowers that you address?
Thank you, PC. So the question is, what's a good fit for us? At the moment, the system is designed for low voltage AC motors up to 690 volts. And medium and high voltage will be likely launched towards the end of Q1 of next year, of 2020. So we'll have a solution for those motors as well. It's around certification and stuff like that. Then next question, typically, and I can feel that you wanted to ask the next question is, are there any other requirements? Well, a motor needs to run at a somewhat stable state for 5 seconds sometimes. So it can have high variancy in load and speed and so on, but the samples that we take need to be 5 seconds of relative stability. So, a relative stable load for those 5 seconds, and we need to have some of those moments from time to time. So, these typical robotic motors that have very very shaky sort of stuff, that's not our thing. But pumps, compressors, most of them will run stable for 5 seconds every hour, at least sometimes. And that's pretty much it. All right, another, okay, we got here. Yeah, right, so, and in closing, Tim said it's not so much around technology, it's around value. And we like to agree with that, and we also say, big question is, how will it change my day-to-day operations? What will change for me as an asset owner? And I think a big insight for us came in the first year of existence for our company, when we went into I think it was a paper factory. My co-founder Gerben went in there and he did a round with one of their condition monitoring specialists. And the guy went in at 8 o'clock in the morning. He had to wear his running shoes because he had to inspect 30 motors that day or 30 assets that day. So he came in very early, took a couple of minutes per asset to take those measurements, finished those measurements at 2 or 3 in the afternoon, did an analysis on them, emailed the report. And what he found during that analysis is that on that single day there wasn't an issue with any of those motors. And that's the point. The problem that you're typically wanting to solve with technology, with condition monitoring, albeit online, albeit manual, is that not so much that your assets will fail very often, but the problem is that if they fail, it's highly expensive. And that justifies an investment into making those rounds, even though you may expect that most of the assets that you'll visit and or inspect will be perfectly healthy at that moment. And you do it still because if they fail, they're highly expensive. So, and schematically, basically you don't know what's going on with your asset base until you visit them and until you start inspecting them. And when you look at the value of condition monitoring, and I advocate for using our stuff, I have a vested interest in you using our stuff, but by and large, whether you use our stuff or any others, condition monitoring or online condition monitoring will help you address, for instance, the issue that 30 to 40 or 50 or even more of your technical team will leave or will retire in 5 years from now. And so any good system will tell you if it's healthy or not. If it's healthy, why not let it run? Why would you waste time and energy on inspecting it or repairing it or replacing it when it's perfectly fine? And even if you detect something that's going wrong but you're not sure, you can focus on those and you can use your domain knowledge and your expertise to help the algorithms develop and inspect, is it right that there's an orange light? And even better, when we detect a failure and even when we know what the exact failure is, you can visit the asset and do the work. And essentially what it means is focus on orange and red, be efficient. And it's not only that you're more efficient from a sort of an almost financial point of view, but you can simply do a lot more. So you can either have more assets that you have in your span of control, so to speak, but it also means that your work will get a lot more interesting. Because when you visit an asset, you know there's something wrong, you know there's something to optimize, and you can use all that knowledge that you've accumulated over the years to make a difference, not to verify that your asset is otherwise healthy. So that was a key insight for us. And I think when it comes to the question, how does it change my day? All things being equal, and in fact, obviously there's an interesting business case behind it, but that's financial. From your own perspective, how will it change my days? I hope it makes your work more meaningful.
Are you finding that your clients are eliminating time-based preventive maintenance tasks in place of this?
Yes, we have to earn that, but yes. Typical for clients in the early days of our company, they would do both, right? So they would install it and they would even let machines fail, even though we said it's going to fail. They said, yeah, let's do it. Let's see how far in advance you would detect it. Nowadays, typically, when we say something's failing, they're not even inspecting, they're just replacing. Motors up to 35, 40 kilowatts, there's no use in repairing them, it's more expensive. So then they just, all right, it's failing, fair enough, let's get it out of the way. Simple as that.
Do you have a list of failure modes that you're currently monitoring for?
Yeah, and this is omission on my part, I should have included it here, but from a asset type point of view, pumps, compressors, conveyors, blowers and fans, rotating equipment by and large. We detect mechanical failures such as bearing issues, cavitation, broken fans, misalignment, basically those kind of things. On the electrical side, broken soft starter, all those, electrical is much easier by the way, but all of those things. And collectively, 93% in 2019 so far. So that's a good number, I suppose. Well, Mike warned me about this. I should have included it. I have the list. I'll mail it to you, and my apologies for leaving it out here. But I would be surprised if we couldn't detect it.
Thank you.
Yeah.
Simon, we can put it up on
So it's on my laptop.
a laptop, we can throw it out there.
Great. All right. So I had this dramatic ending just before your question is, I hope it will make your work more interesting. That was also the dramatic ending of the presentation. So I should have maybe done a little bit more to do that. Yeah, a little bit about us. But any questions beside Mike's?
You're going to show the online demo?
Oh, good point. Yeah. Yeah. So, and first of all, when we monitor our assets, yeah, there you go. So this would be a motor passport, very simple information, motor nameplate information. It'll be on SAP. If you have SAP, it'll be in any other system. And we take this data just to give you an idea, or just some of them are used to automatically tune the algorithms because there's differences between, for instance, the numbers of balls in the bearing. If it's 8 or 9, it has an influence of how you see those kind of things. But typically, this is very easy to obtain. We have this analysis of the condition, and with this very simple stoplight signal, so you have a good overview of. Should I act now? Should I act soon? Or, maybe just let SemioticLabs or Avid do the monitoring at this point. If there's an issue and we can solve it, or we know what it is, we'll present it here. So this is a demo environment of live assets. Unfortunately, they're not failing, but if there's a failure, and we had it on the previous slide where it would be more where we had a fault classified, it will be here. It's not running at this moment, but you can track power factor, current voltage in real time, as well as some more trends over time. Let me see if I can get the mouse. Do you guys see it? Is it showing up? Yeah, it's in the bottom. So, and then.
You need me to come grab the Intel box?
Excuse me?
You need me to come grab the Intel box?
No, that's fine. It's I typically work with an Apple system. Yeah. So it's an overpriced machine, but I love it. Anyways, we have more views, right? So you can combine patterns and look at them over time and things like that. This is actually a cooling system of a cafeteria, so you can see it. It's out at night, and it's probably a weekend, and it's been offline for quite a bit. It's some older data as it's demo. But we can also look at other things like these. So these are sort of heat maps, and then if you want to click on one of those, you can go here. I think what's interesting here, for instance. Maybe this is not, let's assume you have a conveyor system and you monitor 3 motors of that conveyor system. Then this would be weird, right? How is it possible that this one is running and these are not? So those kind of things, our task is to provide you with the information, and with your in-depth knowledge of your system, you can make sense of it. We are working on smart alerts that you could provide yourself. Again, it's around, from our perspective, it's around scalability. So we can offer you the tools to take your domain knowledge and your knowledge of your process to really create an application that's better suited for your environment. So you could say, these guys always have the same jobs for us. So if one of them is running and the other 2 are not, I want an alert. Those kind of things are what we're working on now, and also discussing with the guys from Avid how we can make that useful for you guys.
Can you go back to the screen where you were showing the voltage and current?
Yep.
I thought I saw something.
Now, the problem is scaling, right? So that's what you have here. If you want to scale these, you want to have multiple metrics in the same, it must visually appeal. So I think there's room for improvements in some ways, but that's something we can.
When you dragged across, it looked like you had voltage but no current or power.
That's probably not possible.
Right. That's why I thought it was wondering.
Yeah, I don't think that's the case, but since you're challenging me.
Well, unless you're installed upstream of the grid.
Oh, I lost it. No, so there's always.
Okay, I was dreaming it, all right.
Yeah, all right. Phew. Thanks. We practiced this, by the way. You were going to challenge me and then we would say today, right?
You guys may not know we practiced this earlier.
Yeah. Exactly. So, yeah, that's it for me. Any follow-up questions from you guys? All right, and thank you very much for your time. I appreciate it. Thanks.
We have lunch outside, and I think there was in the invite, there was a prize to be drawn for. You want to draw? Or I draw? I'm the drawer? All right, so these are company names here from Avid. This is ours, S&D coffee, you get a free monitor. How long are you there for? For a year. For a year. One asset for a year. For a year. One asset for a year.
Excuse me. Maybe probably they said it in writing.
Anyway, I hope this was hopefully this was informative. I hope you guys got something out of it. Feel free to contact myself, Mike, for anything we can do going forward. And lunch is outside.
Thank you.